crack the secret code, and you enter the exciting world of mystery, adventure, and espionage. So what am I doing? I'm playing a game. Cryptography. Encoding and decoding secret messages. To play, you have to know language and math and how to use a computer. You can play it with ciphers, where one letter substitutes for another, or with codes, where groups of numbers mean certain words or phrases. At least that's what my dad says. And when it comes down to it, he should know. I mean, code making and code breaking have been in my family for generations. Take my great-grandpa Jacob. He worked for the British during the First World War, cracking the famous Zimmerman telegram. Never heard of it? Well, it was sent by Arthur Zimmerman, Germany's foreign minister, to the Mexican government. His plan was to get Mexico to back Germany in a war against the United States. If Germany won, Mexico would get Texas, Arizona, and New Mexico. It was the British who intercepted it. They assigned their top codebreaker, Nigel de Grey, and a team of coding experts, which included Great-Grandpa, to break it. They had lots of code to work with, and that was the key. You see, code breaking depends on repetition, so they used statistics and a knowledge of German to break the code. I remember when I was little, Grandpa used to tell a whole bunch of old war stories. He used to be with Army intelligence during World War II. He told us that we'd already cracked Japan's code long before the war started, and we knew they were going to attack somewhere in the Pacific, but we didn't know where or when.
Yesterday, December 7th, 1941, a date which will live in infamy. The United States of America was suddenly and deliberately attacked.
Pearl Harbor shocked everyone, and once again, we were at war. During the war, machines did most of the work. It made secret messages easier and faster to make, but harder to break. Top cryptographers like William Friedman and hundreds of others worked day and night trying to read bits and pieces of the Japanese codes. Victory or defeat in the Pacific depended on what they could decode. The turning point of the war came when Navy cryptographers discovered Japan's secret plan to invade the island of Midway. Admiral Nimitz, commander of the Pacific Fleet, called the Battle of Midway a victory of intelligence and recommended lead cryptographer Joseph Rochefort for special commendation. After the war, the spy game continued, so cryptographers like Grandpa were kept busy. But now the world needed a whole new kind of coding expert, mathematicians, like my parents. In the 60s, my dad worked for the U.S. Post Office. His job was to help create a zone improvement program code. You know, the zip code.
Hi, this is Ethel Merman to tell you about the Post Office Department's zip code. It's a new coding system for addressing your mail.
It started with just 5 numbers. The first number codes the region, the next 2 a sectional center in the region, and the last 2 a post office or a town. But as the country grew, so did the mail. By the 1980s, the Postal Service had to add 4 more digits, barcodes, optical scanners, and computers, all of which depended on the binary system. Here's how it works. The post office created a code book. Each decimal zip number is coded in binary, you know, 0s and 1s, so it can be written in barcode by a computer and read by an optical scanner. Remember, this is a code and not the way you count in binary. Here's my zip code. In binary, it looks like this, except there are no spaces. I left spaces between each code number so it's easier to read. Now look at the barcode for my zip. Take out the first and the last long lines. They tell the scanner where to start and stop, but they're not part of the code. The long lines are ones, and the short lines are zeros. So you can see how binary code is written as barcode. Of course, there's always a chance that the scanner will misread one of the lines. So one of the mathematicians on Dad's team suggested they add a 10th number, a check digit, as a way to detect errors. Here's how it works. You add up the first 9 numbers of the zip code. Okay, it's 33. Then select a 10th digit so that the final total is divisible by 10. If the total is not divisible by 10, the computer knows there's an error. It then ejects the letter, which is then sorted by hand. By the way, the Postal Service isn't alone in using this stuff. There are barcodes with check digits used all over the place. But to mathematicians, check digits were just a beginning. Soon, codemakers were inventing coding systems that could not only detect errors, but could correct them as well. Back in the 70s and 80s, my Aunt Jean worked on one of the most exciting coding operations of the century: space communications. How could pictures, data, be sent through space millions of miles without any errors? The answer came from one of the greatest mathematicians of our time, Claude Shannon. Back in World War II, Shannon was working in cryptography at Bell Labs. He soon realized that repetition, words, letters, numbers repeated over and over and over again, was the basis for making and breaking all codes. With enough repetition, you could get the message, even if something were left out. Though he never designed any encoding or decoding equipment, Shannon set the stage for sending coded messages through space. And though there might be errors due to noise, if the messages were encoded with enough redundancy, they could be recovered by a decoder at the other end. Did it work? Well, thanks to Shannon and other mathematicians, like Richard Hamming, hey, it's a whole new world. Using codes, we can compress information and send data faster and more accurately than ever. Codes make it possible to have high-definition television, computer games and graphics, CDs, modems, cellular telephones, fax machines, not to mention live pictures from space. In fact, they've become so common, you might say we take them for granted. Of course, there is a downside. You see, right now, there are people out there, hackers, who might look into our most closely guarded secrets. Without our knowing, hackers might steal from our bank accounts, make long-distance calls on our telephone cards. They might even check our medical or driving records. Our credit cards are at risk. All because they know how to crack the codes and break into the system. A group of mathematicians and computer scientists are working to prevent that. It's a system called public key cryptography. In the past, cryptographers encoded a message using a private key and sent the message out, knowing that it could only be decoded by someone who had the same key. But public key cryptography is really different. It's easy to get information in, not so easy to get information out. One version of public key is the RSA code. It's named after 3 computer scientists at MIT, Ronald Rivest, Adi Shamir, and Leonard Edelman. It's based on the idea that some mathematical processes are easier to do than undo, like multiplying two prime numbers. What's a prime number? Well, they're numbers that are divisible only by either the number 1 or themselves, like 3 or 5 or 7. For example, take two prime numbers like 101 and 149. Try multiplying them. Time's up! The answer is 15,049. Not too tough. Now try and figure out what two prime numbers you would have to multiply to equal this. Give up? And if you think that was hard, try this. Get the idea? You can tell anyone the product of the two primes. That's the public key. But only you know the two prime numbers. That's your private key. Even a supercomputer would take so long to crack this code that no one would want to hang around. It will make it possible to use credit cards, write checks, and keep records with safety and security. So as far as all you hackers out there are concerned, hasta la vista, baby. Look, we gotta face it. The world we're gonna live in, the world of the 21st century, it's gonna be digital. A world of numbers, computers, and codes. It means we'll be able to do things we've only dreamed of. But we gotta understand it and be ready for it. I'm ready. Are you?